Now, next speaker, Konstantin Pankrashkin from Oldenburg, will speak on MIT back operator in most convex domains.
Okay, so thank you, Michael, for the introduction and actually for the invitation to participate in the program. So in a sense, I'm actually disappointed in advance by my talk because in a sense it's a kind of project which is not finished yet. I mean, so, but actually my hope was to finish it before I come here, but anyway, there were some obstacles, but I think at the end, from time to time, one can also present the state of art in some areas, because anyway, there are some reasonably formulated theorems, so that probably makes sense. Okay, so the talk is actually about Dirac operators in Euclidean domains with some boundary conditions. So just to give a context to this MIT bag. So MIT bag, it's nothing but Dirac operator with some special boundary conditions. So, okay. Let us start with some parameters. So let n, it will be my dimension, at least 2. So then I will denote by capital N the following number. So it means that so if n equal to 2, n equal to 2, if n equal to 3, n is 4, and n equal to 4, and so on. But actually, those cases are probably the most interesting ones. So, and I will do it in a very elementary way. So, let alpha 1, alpha n beta be n times n. So Hermitian matrices such that they pairwise commute or pairwise anti-commute. And second, the square of each of these matrices is just the identity matrix n, In. So for people who don't live in the Dirac world, so let me so actually there is a very nice theory about, so this theory of Clifford algebra saying that those matrices somehow essentially, so they are non-unique, but essentially they are unique up to some transformations, but the most canonical choice, if you are in n equal to 2, you take alpha 1 equal to 1, this is, so the Pauli matrices, minus I0, and for beta, you take the third Pauli matrix, which is 0, 0, minus 1. So if you are in the dimension 3, the canonical choice would be that alpha k is 0, sigma k 0, and beta it will be I2, 0, 0, minus I2, and so on. There is some iterative procedure. So in fact, the explicit form of these matrices will not be used in the talk, so actually it's not really relevant. It's sufficient to know that they exist. So, and as soon as you fix some choice of those matrices, so you consider the Dirac operator, which I first consider as just a differential expression with constant coefficient, so which is defined as 1 over n alpha k dkf plus m beta f. So dm, for me, this is just the differential expression. So I'm not interpreting it yet as an operator in some Hilbert space. So it will come in a minute. Okay, this is usually, so this expression is referred to as a Dirac operator with mass m. And the remarkable, so just to make it more clear, so I mean, if it acts on vector function, on vector valued functions. I mean, so f is a so-called spinor. I mean, so if you have a function which depends on small n variables and has capital N components, then and it must be differentiable and so on. Okay, the remarkable property is that if you take the square of it, then due to those anti-commuting properties and so on, you actually have just the usual Laplacian plus m square. No, okay, so if you want to do it correctly, so it's a matrix valued. So I mean, so in other words, is that this is a like local version of the square root of so the Laplacian. But I'm not going to discuss actually some those physics aspects. I'm not. It's so you may ask Raphael, who knows it very well. So just okay. So so what is actually my point? This was an introduction. So what is actually the main topic? So now I take, so let omega be some domain. Okay, some, let's say, reasonable domain, probably bounded. Okay, maybe not really important. Okay, some reasonable domain is such that at least you manage to define the outer unit normal, which is defined everywhere. So, and I will be interested in the following operator, also in L2 omega Cn. Okay, I'm interested in the following operator, omega. So it maps f to dmf. And it acts on functions f which satisfies the following boundary condition. It's minus I beta alpha nu f, okay, on the boundary. Okay, here there is a, so again, okay, for people, okay, the experience shows that there are actually two extremal cases. So people who do like spinor geometry, I mean, for whom it's like, you know, kindergarten, so, or people who never did Dirac operators, so for whom it looks so highly mysterious. Okay, I mean, okay, in the theory of Dirac operators, you often use this, okay, this abbreviation. So if you have a vector x in Rn, then by alpha x, I don't mean actually the matrix multiplication. This is the abbreviation for the following linear combination. This is actually sometimes called Clifford multiplication and so on. So there are so various names. So let me recall that dm is it's a first order differential operator. It means that the boundary condition is actually like a zero order boundary condition. So it couples the components of f which is each other, but there are no like normal derivatives and so on. Okay, and in fact, one should be a bit more precise because in fact, you need some regularity for function f. So at least the minimal regularity, you want this expression to be in L2, which actually guarantees that the boundary conditions of f boundary values are somehow defined. But in order to obtain an operator with reasonable properties, so typically you have those regularity issues. You must assume that f is somewhere in H1 or in some Sobolev space. So actually, what is exact regular? So the question is which regularity of f, okay, of f's guarantees the self-adjointness of the operator m omega. So, and this operator a omega m, this is actually what I mean by the MIT bag operator. So it was introduced in, I don't know, like maybe in 60s, 70s as a confinement model for, so in relativistic physics. And in principle, somehow the general idea that the Dirac operators with those boundary conditions is should be considered as an analog, is a relativistic analog of the Laplacian with Dirichlet boundary conditions. But okay, I mean, no, I mean, say, okay, you have a function. Okay, let's say you assume that everything is defined not everywhere, but okay, at some. Okay, let's say okay. Let's take some, let's say, s on the boundary. Then you have the normal vector, which is, say, an S in Rn. It means that if, so, and actually the boundary condition at S, it would be like minus beta alpha mu S f of S. This is an n times n matrix. Then you multiply by beta, it gives another n times n matrix. And no, there are no derivatives because you only have a first order operator because the normal derivative is not defined actually. So it's a pointwise coupling of components of f because they're coupled. I take yeah, in one component it will be Dirichlet, of course, but in fact one component is excluded. I mean, yes. That means, but it's important this only takes place at the boundary, not in the domain. In the domain, there are no couplings between the components. Okay. And as I said, this is the idea is somehow that it's a more or less a relativistic analog of of the Dirichlet Laplacian. No, but it depends on which f you consider it. I mean, we will get to it because it's actually, in principle, this is a question I'm going to answer for some. So I'm going to discuss it in greater detail. So, okay, at this point, one should think what is actually okay. The Dirichlet Laplacian, what does it stand for? I mean, when you always the frequent interpretation that you assume that somehow you have an infinite wall at the boundary, non-penetrable wall at the boundary. But one of the possible interpretations is as follows: that I mean, this operator omega d, this is defined as somehow some suitable limit of if you take, say, the Laplacian in Rn, and you put a potential which is 0 in the domain, but is very big outside of the domain, and you send m to infinity. So in principle, so there are so the limit, of course, because those operators, they are not in the same space. You need some identifications and so on. Okay, to be honest, it is. To my knowledge, actually, it's really justified only if omega is Lipschitz. I mean, so if omega is Lipschitz and bounded, then this is actually one of the standard applications of the so-called monotone convergence. Okay, if you're non-Lipschitz, to be honest, I'm probably not up to date. I mean, this topic, but Lipschitz is already good. I mean, so. Okay. But anyway, so Dirichlet Laplacian, how do you define it? So you may define it in principle. The abstract definition is very easy. I mean, you take what is the domain of this? It's f in L2. No, it's in H1, 0 omega, such that the Laplacian of it in L2 omega. This is actually the most general definition of the Dirichlet Laplacian, and due to those Lax-Milgram theorem and so on, you know that this always produces a semi-bounded operator, which uses a theory of quadratic forms and so on, so coercivity and so on. So unfortunately, there is no, or let's say, up to now, people didn't find any analog of this for Dirac operators, which would allow you to write something and be sure that everything works. So, because operator is not semi-bounded. Okay, so what happens? So anyway, I am of course not the first person who looks at this problem. So let me mention. So let me give some credits. I should be careful because some people are in the audience. So, okay. So of course, I mean, so at the end, what you have. So what you have here, you have actually differential expression, and you may easily check that this differential expression is actually elliptic. I mean, so in a sense, there are many thick books about elliptic problems in smooth domains, I would say. So if you study them attentively, there are good chances that you find some theorems. I mean, so just okay. If you are okay, if let's say omega is smooth, okay, I would also assume that actually omega is always bounded. Okay, to avoid some weird cases. So I think it's okay. So if the omega is smooth, but okay, I think actually someone who attracted, yes. Okay, okay. Thank you. Okay. So I was not sure. Okay. So if, no, but sometimes, you know, I'm not sure if it got stuck or I should push stronger. Yes, okay. That's okay. Okay. Okay, but okay, smooth, which is okay. Let's say if it's something between C, it's something between C2 and C infinity, I would say. So it's I would say in general theory, people would assume usually C infinity, but if you get to specific operators, usually you need just lower regularity. Okay, there was a paper by Ben-Gurion and other people who are not here, so. Okay, but anyway, I know it's Soren Fournier, also Gerda Stockmeier and Anne van den Bosch. Okay, 2017. Okay, they considered the case when n equal to 2. And okay, and they have shown that the operator A omega m is self-adjoint on the so what I call H1 domain. It means it's so the function f in H1 omega Cn such that the boundary condition holds. So by the boundary condition, I always mean this one, because there is just one boundary condition. I don't want to recopy it every time. And actually, anyway, this is so the machinery was actually rather specific because then there was some Hilbert transforms involved and so on. I mean, so it's actually, let's say it's not for free, I would say. Then, okay, in the dimension 3, there were the paper by Romier Bonafos. Yeah, unfortunately, all people have very long names in this theory. Bonafos and Luis Vega. It was, I think, 18. I think okay. There were some subsequent works. Okay, they actually have shown the same result also in 3 dimensions. Okay, to be honest, this result was actually a bit more general. They considered slightly more general boundary conditions, but I would like to stick to just to this one. Okay, but okay, if everything is okay, it's actually both. Okay, let's say still for the smooth case. Okay, and so in fact, at some point we also revised some literature. And in principle, if you are C infinity, it was our work with Moroyano, Bonafos, and P in 20. So it also holds for all n if you are smooth, because at the end we have found that this specific case actually was covered by some papers so about Dirac operators in the context of spin. Okay, I mean those spin structures. Okay, now the question which is of interest is why if it's what happens if you are non-smooth. Okay, I should probably add that, okay, if you are bounded and if self-adjoint on these domains, then automatically you have a compact resolvent. And in principle, there are some also questions related to spectral optimizations, but I think none of them is answered so far, but I will get to it also. Yeah, I mean, this is in the smooth case, it's an elliptic boundary condition, yeah. Okay, in the non-smooth case, okay, the first thing is that It was work by Letroist and also again Amir Bunachotz in 2018. And it was again for the two-dimensional case. If omega is a non-convex polygon, then AM is not self-adjoint on this and H1 domain. Because in principle, if you have an elliptic operator of first order, the first idea would be to start with a Sobolev operator, with the first Sobolev space. But okay, it's not self-adjoint, but okay, in a sense, it's because it has the finite deficiency indices. So it means that you must extend the domain in order to obtain a self-adjoint operator. By the way, this is actually those issues, they are also known for the Dirichlet Laplacian. For example, again, if you are in a smooth case, I mean, if omega is smooth, you may rewrite this condition as f is in H2 omega such that f is 0 on the boundary. Or, okay, or maybe you may write, okay, I will write it in this way. But if you are in a non-convex, for example, for the case of non-convex polygons, the Dirichlet Laplacian is not self-adjoint on this case. It has deficiency indices, and the number, and actually the deficiency indices, these are exactly the number of concave corners. In other words, if your polygon is convex, everything is nice. But if not, if you should count, but somehow it's more or less the same technique. Somehow it's like manual computation. Somehow there is, as soon as you have boundaries, you cannot compare your work with everything with the half space. So essentially, you need to work all the cases one by one. Okay, but then later, there was a paper by Pizzichillo and Van den Bosch. I think it's again, I'm not sure about the year, maybe 19. Okay, but anyway, around those years. They have shown the following, that if omega is any, let's say, curvilinear polygon, then the operator M, this omega is always self-adjoint on the so-called H1 half domain. What I mean by that, these are functions which are F1 half, such that if you apply the Dirac operator, you are still in L2, and the boundary conditions are satisfied. Because this is okay, because I mean, again, the boundary conditions, they are defined, boundary values are defined by duality and so on. Okay. It's not self-adjoint on this domain. It's not, its domain is not in H2. It's self-adjoint on this domain, but this and this, it's not the same. In the smooth case, it's the same, but in the non-smooth case, yeah, in the L-shaped case, it is not self-adjoint on this domain. But it's always self-adjoint on this domain due to Lax-Milgram theorem. But here there is no H2, so no, it's at H2 that you lose, so roughly speaking, you lose the H2 regularity in the L-shaped case. So this is how it's usually formulated. You need, at this corner, you need to impose some, like a kind of radiation condition to take, and there are many possibilities for that. Okay. Mm-hmm. 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 Okay, but anyway, okay, at this point, one may actually ask a question why both are actually probably those are issues. Why do you need whether you H1 half or H1 at the end if you are also in this case, you get a compact resolvent, some reasonable operator, and so on. So actually, why is this aspect important? Okay, there is at least one point where this aspect is really important. If you are, okay, if omega is smooth, there is a nice formula for the square of this operator. And this looks as follows. So where is it? It's the integral of omega f squared plus m squared. Okay, sorry. It's f squared dx, and then plus integral of the boundary plus h1/2 ds. Yes, so it looks actually quite nice. So H capital, this is the mean curve. Okay, this is defined. Okay, this is defined as the sum of the principal curvatures. I mean, so. Okay, assuming that it's non-negative if you are convex. And actually, this is one of the main tools in. So in fact, probably the most interesting case it's when this m is 0, then okay, many terms cancel, and actually this is a kind of still open question. If you assume that, let's say, mass is 0, or you may consider it also for general mass, so which omega, and assume that omega is, let's say, the volume is fixed, or okay, something is fixed, which omega would minimize the first eigenvalue. So this is, okay, for Dirac operators, it's actually, to my knowledge, there are no reasonable results so far. I mean, there are some estimates from above, from below, for the principal eigenvalue, but somehow none of them produce isoperimetric results, I mean, so in the classical sense. And okay, actually the only strict result I know is that if let's say if you consider like rectangles, then the square minimizes the first eigenvalue, but it's actually not for free, because even in rectangles, the Dirac operators has no separation of variables. I mean, so you need to do some specific cases, and actually, this formula is reasonably nice. I mean, because here all those matrices cancel, but actually they don't disappear because they are in the boundary conditions. There are not all the matrices are now in the boundary condition. It's actually what makes the problem very difficult, because I mean, if you deform omega, your boundary condition kind of changes. But anyway, the quadratic form is somehow relatively simple. And if you look carefully at this expression, it's clear that actually if you want this formula to be valid, you must have H1 regularity. Because if you are not in H1, simply this form is not defined. So it means that, for example, if you have non-convex polygons or something, or let's say in general non-smooth domains, this formula is wrong, which is not good. I mean, so you want this formula to be validly. For example, if you, okay, in 2 dimensions, actually, you may prove this. If you have a convex polygon, then then you still have H1 regularity, and actually you may prove it by hand. I mean, just for H2. But if you go to higher dimensional case, it becomes tricky. Yes, please. What do you mean exactly?
Like, do we know
No, but I mean, in 2 dimensions, if you have a convex polygon, this formula still holds. Non-convex, no, I don't know. I mean, no, just I don't know. Because the mean curvature goes to -infinity, and you need to use. Did you want to ask anything? No, but I think I would say my point is that actually I think we agree that if you H1/2, this probably not defined. I mean, so that's gradient is not in L2. I mean, so I would say. But okay, let me now mention, okay, I mean, here that's everything is more or less, but I mean, at technical level, I mean, it looks, for smooth case, it looks well understood, but okay, for non-smooth case, it's somehow, it's still open. And now let me mention what I mean by that. I mean, the relativistic analog of mechanism. It's again, at the moment, it's only done for smooth omega. So if omega is smooth, okay, if omega is smooth, okay, then there are many results of the following type that, but okay, I will write the simplest versions. And for each j and n, so it's actually quite nice to work with squares. It is the limit when m goes to infinity of the respective eigenvalue. Okay, but I will write it now, mm omega squared. Okay, what is this? It's again the operator in okay, the Dirac operator in Rn, and then you have m beta, okay, sorry, 1 over c beta. So it means that you consider the Dirac operator, okay, without minus, I mean, you consider the Dirac operator in the whole space, but okay, this term, you may interpret it as follows, that you put a large mass outside of omega. So enter, there are results, there are also results of the type resolving convergence, but okay, but I mean, the philosophically it means that, I mean, this operator is, can be viewed in some sense as the limit of those Euclidean, just operators in the whole space without boundary conditions. But again, it's for the smooth case, and actually all proofs I know, they are based on this expression, actually, because in fact what you do, you compute the square of this thing, and you look at what happens outside of omega, and if you cut off, essentially you come here. I mean, so this is general idea. So, but as this formula is problematic for the non-smooth case, actually there are no, to my knowledge, there are no results of this type for non-smooth omega. Okay, I'm not aware of any result, I would say. So this is a good. For Dirac operators, I don't know, sorry. It's, okay, there are some other popular boundary conditions with very weird properties, but I was quite happy to understand this one, to be honest. I mean, how can I erase stuff? Huh? Ah, okay. Okay, thank you. Yeah.
Very basic question. Can you give some intuition how it comes? Because it looks quite specific to those who are not familiar with it. But can you multiply it by 2 to the right hand side?
No, you may multiply it by any scalar function. You may multiply your function. So, for example, you may apply. It must simply commute with the matrix multiplication. So, I mean, you may apply, let's say, a cutoff, but the cutoff it must be scalar. This is actually, yeah, it's a good point actually. So you may multiply it by a scalar function, no problem. I mean, yeah. Okay, but now let me finally formulate 3 theorems. And probably I will even manage to say some words about some proof ideas. Okay, there are 3 theorems. Theorem 1. Okay, let omega be so bounded convex. Then this operator omega is self-adjoint on this H1 domain. okay, I will write it again. I mean, this f in H1 omega Cn such that the boundary condition holds everywhere, or almost everywhere. Because if you are in the, it's okay, just for people who are not, who don't visit the convex world very frequently. I mean, okay, the convex domains, they are always Lipschitz. I mean, there is a bounded convex, any bounded convex domain is Lipschitz. It means that the normal vector is defined at least almost everywhere. So, and it means the boundary conditions should hold almost everywhere, which is actually quite mysterious because, I mean, if you are H1, because if you look at this, I mean, it looks very weird because this factor is actually rather bad because it's not, as soon as you multiply H1 function by this factor, you are not in H1 at all. So it really holds. This is very mysterious that this produces a self-adjoint operator. Okay, let us continue. To continue, let me introduce a definition. Because to do the rest, I couldn't do it just for general convex domains. I need something just a bit more. Okay, S, a point S on the boundary is called singular. Okay, let's say doing. So the singular boundary, also boundary of omega, is defined as the set of the points on the boundary such that omega does not coincide with a smooth domain near S. Okay, I think this is actually a rather obvious definition, but I mean, but okay, well, it's like if you are a polygon, these are vertices, and so, okay, in 3 dimensions, it's a bit more involved. Okay, and I say that by definition, I say that omega has a piecewise bound, so piecewise smooth. Okay, smooth, it means by definition that the singular boundary is contained in the union of finitely many compact n-2 dimensional submanifold. Okay, this again, this is okay. I mean, so essentially, if you are in 2 dimensions, it means that you only have finitely many singularities. So think about polyhedra, I would say. So something like polyhedra, it's okay, or curved polyhedra. I mean, this is okay. Okay, and for the second theorem, I need this assumption. So if let omega be bounded convex, okay, piecewise smooth, then one has, okay, for any f in the domain, okay, one has the same nice formula for the squares, which is, okay, this is integral so you have the same formula as before, which is actually like kind of just a small technical improvement, but anyway, not so obvious. I mean, again, the mean curvature can define it only almost everywhere and not at every point. No, but you are in H1. No, but I mean, you are in H1. I mean, so it means that I would say this is probably the easiest part of in all this analysis. Okay, and theorem 3 says that if you are bounded convex piecewise smooth, and here is a very weird assumption that H is bounded. Okay, then one has, okay, this, okay, I will not copy it because, okay, then one still has this relation for the idea. So one can actually show this result also for this class of non-smooth domains. Okay, I do not like actually this assumption, but somehow I didn't manage to get rid of it, please. No, I mean this factor, if you multiply, okay, I mean, if you have a function in H1, if you consider its boundary value, it's in H1 half. But if you multiply it by this strange factor, you leave H1 half. So I mean, it's so it has it's very tricky. I mean, so this is actually the whole problem. I mean, the analysis that you cannot do anything in H1 half, so you must jump between various spaces. But okay, then you have this. Okay, I mean, false. And this seems to be the first, actually the first result which interpret the eigenvalues of this operator in the non-smooth case as like infinite mass boundary conditions. Actually, another, just a moment. Another way, actually, there is an alternative name for MIT bag. It's actually infinite mass boundary condition, especially actually due to this result. No, it's not. It's not obvious, and actually, it's not discrete. I mean, so what I mean, but I mean, its essential spectrum goes to infinity. I mean, so it means that like there are more and more discrete eigenvalues appearing. I mean, and the essential spectrum goes to infinity due to this. Okay. And okay, I was told that I can use up to 55 minutes, so I will abuse this rule. And so why not? I think from time to time one can do some proofs. I mean, but just, I mean, to just, okay, this is what I'm going to show. It's actually kind of very elementary, but for me it was really enlightening somehow, because where I actually managed to understand why the convexity is interesting. And this is also one point when I realized that it's useful to read books from time to time. I mean, because unfortunately, it's not sufficient to buy a book. You need to open and to read it. I mean, this is a serious drawback. Okay, as a proof idea for theorem 1. Actually, this theorem 1 looks actually very boring, but actually it's more important than the other two for me, because it's actually, this is kind of something fundamental. Okay. So the first observation is that this operator A omega m is symmetric on the H1 domain. So this is something which always holds. I mean, it does not use the regular. In the Lipschitz case, it's also always true. You may integrate by parts. The problem is it means that in order to show that it's self-adjoint, one need to show that the operators am plus minus I are surjective. So as soon as you show that they both are surjective, then you are self-adjoint. Okay, here I do some, okay, actually the relevant case is actually just m equal to 0, because it's just added bounded perturbation, and I denote by A this operator A omega 0. Okay, now, so how is, the main point is actually how the convex case related to the smooth case. Actually, there is, okay, this is probably, okay, the idea is that there are, okay, maybe, actually, last year there was even a conference about so convex something and spectral optimization or whatever. I mean, so probably so people actually learn it more than I did. In fact, there is a result of the convex analysis saying that one can approximate omega, okay, from outside by smooth convex omega p. Okay, I'm not going to specify because actually what do we mean by approximation? Actually, this is actually like typically theorem which occupies 2 pages in a book. I mean, saying that there are local charts such that you may cover that in some local charts there are some functions which converge like uniformly and something converge pointwise. Okay. But one of the consequences is, for example, that the Hausdorff distance between those goes to 0. But actually, there is much more. I mean, so actually, the Hausdorff convergence of convex set has many nice consequences. So you have like omega, which is kind of non-smooth, but you may approximate it from outside by smooth omega p. And you know already that you have very many nice results for smooth domains. So, okay, now let us start considering proving the surjectivity. So, for example, just with plus, I mean, just to make it more readable. Just a moment. Okay, we do it by definition. So let G be a function in omega. Okay, this is actually this must be Cn, but I will actually remove it from now on because. So to show if there exists a function, or to check if there exists a function in the H1 domain, such that am omega plus okay, so this operator a plus f is equal to g. This is actually what I'm going to check. Okay, and for that you consider the following. We will use this approximation. So I extend it by 0. So I obtain a function gp which is in L omega p. I mean, so just here I have my function g. I extend it by 0, and this function has, of course, the same L2 norm. Okay, but now we know that the operator AP, which is, okay, this is again omega p 0, is self-adjoint. And it means that there exists a unique vector fp, okay, in this domain, okay, in this H1 domain on omega p, such that AP, okay, maybe I will AP plus IF is equal to this extension by 0. Okay. Okay, now we do very involved computation, okay, which I actually probably it will be my last point actually. Okay, this is of course the same as the L2 norm for the 0 extension. Okay, then you write it as AP plus I F of omega p. Okay, but here we use our nice formula. P plus m squared. Okay, there is no m actually here. Okay, this actually square comes from I actually. Okay, dx, and then there is this term. I mean the omega p, and here there is the respective mean curvature. Okay, and at this point actually it's time to use the convexity, because if you are convex, this is then 0. So I mean it says bigger than the norm of fp square in H1 on omega p. So it means that those norms are bounded, because at the beginning you started with just some constant thing. But it means that, okay, that it means that the function, so if you now restrict those functions back to omega, because those functions, they are on a bigger domain, omega p, then this fp, it will be, of course, in h1 in omega, and it will be again bounded. And okay, then there is, so then with the subtraction of subsequences and so on, you may assume that it converges weakly to some functions in h1 and omega, so which automatically in h1 of omega, and actually you need to, this is actually a good candidate for that. And in principle, at this point, you need to do some very boring computations saying that, okay, you can easily, it's like almost by definition, you obtain this condition. I mean, that if you apply the Dirac, you obtain G, but actually you spend some time by showing that this function satisfies the boundary conditions. This is a kind of, because, okay, at this point, it's actually, there are some like 3 pages of computations, because in principle, the idea is that you want to like compare the boundary values of Z with the boundary values of this function on omega, but these are different spaces. But anyway, due to the fact that they are convex, you can identify them by in some local charts and so on. So I mean, at this point, you actually need to switch to local charts and do some, estimate some integrals using like Cauchy-Schwarz, so like 5 times. And so you obtain some, okay, this is not presentable in a seminar, I would say, so, okay. But then at the end, but the good thing is actually to show that, to find a candidate for this function f, and actually it comes from here. So actually the convexity is actually used only at this point. So in principle, if one revises the proof, one can see that it can be actually adapted to slightly, actually there is a, but okay, I mean, as I said that, so this involves a very specific approximation of convex domain by smooth domains, and as soon as you may have it, you can do it, replace convexity, let's say, by mean convexity, but I don't understand what type of domains you have then, I mean, because, but as soon as you have the same time of approximation by mean convex domains, then, or even not mean convex, but just if you have a universal lower bound for the mean curvature, I mean, one can do more or less the same. But in particular, this would work for curvilinear polygons without concave corners. Because, but anyway, I mean, here I skip it because at this point I'm actually supposed to, okay, I mean, with presentation I would show like a theorem of 3 slides, but I don't think that it helps anyone. I mean, to see it. I mean, so okay, and this is actually the current state of things. I mean, for the third theorem, what is actually nice is what is used actually is the following result. If you consider the exterior of a convex domain, then you have a very nice inequality that if let's say U is in H1 omega C, then you have nabla U squared. Okay, plus gamma squared U squared dx. It's gamma. So this is actually a very nice inequality. So it's actually just for Robin type operators, which is very nice because so essentially it's one-dimensional inequality which you apply just on each half line. So it's then collected using kind of. And actually, this actually helps a lot when proving theorem 3. And here it's again, but okay, it's not literally that because at some point there is some mean curvature which appears in those expressions, and it's exactly the point where I need its boundedness because otherwise it's everything fails. So So an interesting point for me, it was also to learn that actually in the convex case, if you are piecewise smooth, the mean curvature is not obliged to be bounded. And it, let's say ChatGPT produced a very simple example. Huh? Yeah, it's good. No, but actually it's very simple. So if you consider just the graph of the function, say x over 3/2, then its curvature near 0 goes to infinity, because the curvature is like the second derivative. But the mysterious thing is actually, even if it's unbounded, this integral is always bounded. This is like, this integral is always well defined, which is highly mysterious for me. I mean, just, I don't have no explanation for that. I mean, but okay, I think I should stop abusing the schedule, and thank you for your attention.
Questions or comments, please?
So you said it's still ongoing because you hope to prove much more than this, or?
Okay, to be honest, no, in fact, my current interest is to show, okay, this is, I mean, this infinite mass, to understand it for the Lipschitz case, actually, for the general Lipschitz case, where you probably leave H1, but my impression is that one can still do it. Of course, then what fails, it's those all variational methods, but there are other methods like resolvent analysis. And I would say there is some progress, but it still does not give a real improvement of. I would say, so my impression that with the resolvent analysis one can remove this, but for example, removing the convexity, it's a bit tricky. I mean, just. And actually, I would say that just the self-adjointness in Lipschitz domain, it's, for me, it's not completely clear currently, because there are some, like, it seems that it should be self-adjoint of this H1 half domain, but somehow the way how it's presented in the literature doesn't look very convincing so far. I mean, just I would like to recheck it.
Since the operator is self-adjoint in the bounded domain, differential operator elliptic, there must be some information about sequences of eigenvalues which go to plus and minus infinity.
Yeah.
Do you know something about it?
No, but I think if you are, I don't know, in a smooth case, I think you have the usual while asymptotic. I mean, it's, I don't know, I didn't look at it. I mean, so I'm quite sure that it should be, no, but okay, the best answer I can propose is I don't know. I mean, this I didn't. I would say in the smooth case, it's very classical at the end. I mean, it's a regular elliptic boundary value problem, so there are no surprises. But in the not smooth case, and especially just in purely Lipschitz.
So you said you don't even know that it's discrete, the spectrum?
No, it's discrete, of course. The question was, like, if I understand correctly, about, let's say, while asymptotic. So this is. No, in the smooth case, it's.
In the case when it's not smooth.
No, in the case of non-smooth, to be honest, I'm not able to cite. I think if you just have a Lipschitz boundary, I'm afraid I cannot give you a theorem saying that on which domain this operator is self-adjoint. So it's not yet. I mean, there are some. My impression is that there are some gaps in the literature. So I mean, so only after you define the operator, you would start looking at. I would not expect anything exotic, but it's not, it's like not for free, maybe.
You can also do Dirac on, not this mass Dirac on manifolds. So how easy it's to generalize for dimension manifolds or manifolds with boundary?
No, actually, this is also a very popular topic. No, but okay, what is actually the problem? I mean, so I would say there are essentially two communities which are almost disjoint. I mean, those doing like spin structures and so on. I mean, so let's say global, let's say what's called analysis on manifolds, and let's say people considering Euclidean case with specific boundary conditions. And the interactions between those two is actually quite limited so far, but non-zero. But for example, I cited a paper by Andrei Moroianu. I think it was a good work. So it's something which we managed to do. But okay, but on manifolds, with smooth boundary, actually recently there was a nice paper by Grosse, Uribe, and Han van den Bosch. It's actually published 2025. It's call it like local boundary conditions for Dirac operators. It's actually for domains on manifolds. I mean, but okay, but for the smooth boundary, I mean, for manifolds and non-smooth boundary, to be honest, I never heard about anything about it. I mean, that's. But for me, I would say so far I did not see any work where, let's say, convexity is used for Dirac operators. But anyway, it's very specific for these boundary conditions, because as soon as you perturb boundary conditions and you start having additional terms here, that becomes very tricky, actually. Now, it doesn't mean that it's false, but I mean the method should be completely different, because there was a nice book by Pierre Grivard, actually. It's probably the only book where it's which I managed to read about this topic. And actually, I mean, but then actually, in his case, it's like, say, for Dirichlet, and he did it for Laplacians. I mean, it's like for the Dirichlet case is essentially for free. So for Neumann, you should work. And actually, for the Robin case, it becomes something really real analysis kind of. I mean, but for me, the good point is actually for Dirac, it was actually easier than for the Laplacian, because for the Laplacian, they spend most of the time just to show that the function is in H2, because it's somehow, because roughly speaking, they do the same idea. But here you get automatically a function which is in H1. I mean, you don't need to improve the regularity. And for Laplacian, you get first a function in H1, and then you want to show that it's in H2, and it uses this, how it's called, a Rayleigh-Pogozaev identity with some, I don't know, some mean curvatures. I mean, so you need actually like, you need a kind of uniform control for the norm of the resolvents of the Laplacian in these approximating domain. Yeah, exactly. Yeah. I mean, because what is mean here is that you have a kind of like a uniform bound for the resolvent, actually, if you have a sequence of convex domains. Okay, this is actually the point.
Any further questions? Thank you very much, then.